Alright, this is the second video for assignment number 40, graphing exponentials. So we're going to do a couple more examples of graphing exponential functions, and then we'll also do a very simple exponential application. So here we're going to be first looking at graphing f of x is equal to 2 to the negative x power. So what we want to do is we want to figure out what the parent function is first, and then use what we know about transformations. So this is going to be a reflection over the y-axis, that's the minus x does that, of your parent function 2 to the x power. Now in the previous video we graphed 2 to the x power, I think twice. And we're going to use the 3-point method, so negative 1, 0, and 1. So that gives us 1/2, 1, and 2. And I like to make my graph look nicer, so I might use a couple extra points. 2 squared is 4, 2 to the third is 8. Horizontal asymptote in stock form is going to be y equals 0. So put in that horizontal asymptote, and then I'm going to connect my dots for my parent graph. That's 2 to the x power. Okay. All right, now all I need to do for graphing the transformation is I just need to reflect over the y-axis. So reflect over the y-axis and reflect over the y-axis. This point right here is on the y-axis, so when it's reflected, it stays put. Okay, so we got our 3 points. We can reflect the other 2 points if we so choose, and then we'll connect our graph. And so this would be an example of an exponential decay, the 2 to the negative x power. Now watch, we can use properties of exponents to write this as a base between 0 and 1. Okay, but first we'll mention our horizontal asymptote is 0, and our domain is all real numbers, and a range is all positive numbers. Now 2 to the minus x power, using properties of exponents, that's 1 over 2 to the x power, which can be also written as 1/2 to the x power. 1 to the x power is 1, 2 to the x power would give us the 2 to the x power, so it's equivalent here. Now your base here is 1/2. 1/2 is between 0 and 1, and if your base was between 0 and 1, you had exponential decay. We can also develop a table for this. Okay, so if we use x is minus 1, so again we're using the same x values, minus 1, 0, and 1. So 1/2 to the negative 1. When we had a fraction raised to the negative exponent, we flipped the fraction over and then changed the sign of the exponent to be positive. So this is going to give us 2 to the first power. So that gives us the first point of negative 1 and negative 2. So we got that right there. Then we evaluate it at 0, so 1/2 to the 0 power is just 1. And so that gives us 0, 1. And then finally, 1/2 to the first power is just 1/2. And so that gives us this point right here. So all the points are accounted for there. And so we've graphed this same thing in 2 different ways. Okay. All right. So let's look at number 5, where we have 2 raised to the x plus 4 minus 3. Now if you have something with the x, so the plus 4, that's going to control left and right. So because it's a plus 4, you're going to go the opposite direction. You're going to go to the left. So this is going to go left 4 and then down 3. So we're going to go left 4 and down 3. And what we want to do is we want to base this off of our parent graph, which is 2 to the x power. So what I'm going to do here, not so I don't clutter things up too much, is I've graphed those 3 points, and I did 2 extra points there just to make it nicer, of 2 to the x. I'm not going to connect them for now, so it's a little bit easier to follow what's going on. And then our horizontal asymptote of y equals 0. So that's your stock form. Now let's follow what your horizontal asymptote does for your transformation. So your horizontal asymptote is y equals 0. Now if you shift that to the left 4 times, it's still y equals 0. When you move it down 3 times, then it becomes y equals negative 3. So we do slide that horizontal asymptote down. So the horizontal asymptote is now y equals negative 3. Now you've done transformations before. There's nothing new here. So we're going to go left 4, 1, 2, 3, 4, and then down 1, 2, 3. And then you're just going to do that with all those points there. So left 4, down 3. Okay, and now that we've done that, we can go ahead and sketch And why not we sketch the parent graph as well. Okay. And so that's all there is to it. You want to graph the parent graph, just like we've done before, and then use your transformations to graph the transformation. Okay, let's talk about the domain. Domain is all real numbers. The range has actually slid down 3 units, so it's now -3 to infinity. That's your low to your high. Okay. All right, we're going to take a look at 2 more graphing exponentials, and then a graphing, and not a graphing, but an application problem. So hang tight, we're almost there. All right, so we're going to look at 1/3 to the x power. So the base is 1/3. That's between 0 and 1. So this is going to be an exponential decay problem. We're going to handle it in the same way we've done all the other exponentials. We're going to use the 3 points, -1, 0, and 1. So we evaluate at -1. We have 1/3 to the -1. So flip your fraction over and change your exponent to positive. And so the first point is going to be -1 and 3. Okay, now we're going to do 0. 1/3 to the 0 power is 1. And then 1/3 to the first power is 1/3. So that gives us our 3 points. The horizontal asymptote in stock form is always y = 0 for these exponential functions. Okay, and we got our 3 points. That's enough, and we can go ahead and sketch our graph, label it. And so now our domain is going to be all real numbers. The range is all positives, and your horizontal asymptote is y = 0. Okay. All right. Now the next problem we have, number 6, we're going to graph f of x is equal to e to the x power. Okay. Typically on your calculator, you're going to have an e to the x button and then like an ln. It might just say ln or lnx. And e to the x might be the primary button, and then you would have like a shift or secondary to get to the natural log of x. Some calculators might have an ln button, and then e to the x is your secondary function. Okay, e is called this guy's number, and so maybe it's like, okay, so it's Euler's number, but it's actually pronounced like the former Houston Oilers, the Euler's number. Okay, it was named off of a famous, I think he was a Swiss mathematician from the 1700s-ish. Anyways, so this is a very special number, so your calculator has an Euler's button on the calculator, and it's coupled with a natural log, which we'll get into probably later this week. All right, so if I want to input, for example, e to the -1, depending on what type of calculator you have, you might plug in e and then the exponent, or you might plug in the exponent and then e. It just depends on your calculator. So if you have a scientific calculator, like a TI 30X2S, those are perfect. You would handle it this way, and it's going to be a secondary, and you would do second and e to the x, and then when you hit the ln, so you do the second and the e to the x, you're going to get e and a caret, and sometimes they'll put like a parentheses on there, and then we'll just put in -1 because that's the first thing we're going to do is -1. Okay. Now, if you have a different type of calculator, you would actually, I think you'd have to do it this order. Like let's say you have a cell phone calculator, you hit the 1, and then you'd hit a +- button to make it negative, and then you'd hit your e to the x button. Okay. Oops. So let's take that off. Okay. So I got extra stuff here. Okay. So let's go ahead and set up our table. So x and e to the x power. So -1 and e to the -1. So when I plug when I evaluate e to the -1, I get about 0. It's like 3.6-ish, 367, something like that. I'm going to round it to 1 decimal place for graphing purposes, so it's going to be 0.4. Okay, e to the 0 is easy. That's just going to be 1. Okay, and then we're going to do e to the first power. And e to the first power, e is approximately 2.71, etc. We're going to just use 2.7 for our graphing. So that gives us our 3 points. Stock form, horizontal asymptote is y equals 0. We'll go ahead and connect our dots, label our graph, and then we'll go ahead and mention our domain and our range. The domain is all real numbers. The range is all positive numbers. And our horizontal asymptote is y equals 0. Okay. All right, and the Euler's number, the exponential e to the x, natural log of x, those come up in all kinds of applications. So, if we're trying to model the population of bunny rabbits on a desert island or some sort of tropical island, I don't know, or bacteria growth, compound interest with money, all of those will use exponential e to the x. So we're going to go ahead and look at an application here. And here we have the rabbit population on a remote island is given by the formula nth of t equals 39e to the 0.03 t, where t is measured in years since 1993, and nth of t is measured in millions. And very basic, they want us just to use this model. So what is the rabbit population in 1993 and in 2003? So what we're going to do is we're going to construct a table relating what year it is and t, which is measured in years. And so we'll do the year and then time. So this model starting out at 1993. So in 1993, we're going to start our time off. We're going to say time is 0. And we're just going to go all the way down, very simple. You might say, okay, well, from 1993 to 2003, that's 10 years, so t should be 10. And so we'll build it up this way also. So 90, 94, 95, 96, 97, 98, 99, 2000, 2001, 2002, and 2003. So we're just going to increase by 1 year, so our time is going to increase by 1 year. So 94 is 1, 95 is 2, 96 is 3, and we keep going. Just keep counting down all the way to 2003, which ends up being t is equal to 10. Okay, so what is the rabbit population in 1993? That would be when time is equal to 0. So we're going to plug in 0 in for t. So we're going to do 39 e to the 0.03 times 0. So that's going to be 39, and 0.03 times 0 is just 0, so we got 39 e to the 0. That e to the 0 is 1, so we have 39 times 1. And so it is 39, not 39 rabbits, but nth of t is measured in millions. So in 1993, there are 39 million rabbits on this remote island. Okay, in 2003, your time is now 10. So I'm going to plug in 10. So 39e to the 0.3 times 10 is going to be equal to 39e to the 0.3. So depending on what type of calculator you have, if you have a TI 30X2S, you're going to do 39e caret. It's going to give you a parentheses and then just plug in 0.3. If you have like a cell phone calculator, you're going to do 0.3, and then you're going to hit your e to the x button, and then you're going to hit multiplication button, and then multiply it by 39, and that should give you about 52.6445, and that's going to be millions. Okay. Alrighty, that's it for this video, and we'll see you next time.